Hello everyone, I am Sandeep Bhat. Today I'll be talking about developing a custom load balancer using Go and Envoy that is both scalable as well as fault tolerant. Before we proceed further, I would like to quickly introduce myself. I have 8 plus years of experience in the industry. Prior to my current role, I used to work at companies like Walmart, Cisco as well as Hewlett Packard Enterprise. Currently, I work as a staff software engineer at Harness. Harness is a company that operates in the DevOps space, and I'm part of a team that is focused on cloud cost optimization. As a result of this, I have got exposure to multiple different cloud products like AWS, GCP as well as Azure. Beyond work, well, I love traveling across the world as well as reading upon different tech and exploring new technologies. How are we going to go about during this talk, right? So we will start by discussing some of the basic concepts of load balancing. We will then see what are the different cloud native options that we have. Post that we'll discuss about Envoy, what is Envoy and what are some of the key features of Envoy, some of the components of Envoy that we will be utilizing in our custom load balancer. We'll then see what are the different features that we would want to target using our custom load balancer, and we will discuss about the architecture or the components of our custom load balancer. Then towards the end of the talk, we will also see a working demo of a custom load balancer. So what do you mean by load balancing? Load balancing is a key concept in a distributed computing where scalability, reliability as well as fault tolerance is essential. At the core of it, load balancing is primarily about routing incoming traffic across multiple different application servers, ensuring that they are not overwhelmed with requests and also optimal usage of the resources. So as you can see in this image, you have multiple different users trying to access particular service across over the internet. In this case, you can see a load balancer sitting in between the users as well as the application servers, routing traffic across multiple different application servers. Some of the key features of load balancing would be high reliability and availability and the flexibility to scale. So in this case, the application servers can scale by adding more servers and thus achieve what you call as horizontal scaling. And the performance of the applications are thus improved when traffic is routed or distributed evenly across multiple different application servers. Some of the key load balancing algorithms or commonly seen load balancing algorithms are round robin based load balancing or weighted round robin based load balancing as well as least connection based load balancing. So this is a simple example of load balancing. Like as you can see on the left side of the screen, like you have multiple clients trying to access a particular service over internet, and the load balancer sees that both the application servers are healthy and routes or distributes traffic across both of them evenly. And on the right, you can see that one of the application server has gone down. Now the load balancer recognizes that and routes all the traffic to application server 2. Thus, the clients do not see any difference. They do not notice any. So, talking about the cloud native options, what are the cloud native options that we have? AWS has its own offering called AWS ELB, Azure has App Gateway, and GCP has its own. In this case, we are primarily discussing about layer 7 load balancing. We are not going to be discussing about layer 4 load balancing. In this case, the core idea of load balancing involves 3 major components, or you would have incoming traffic that is being identified in the or processed on using rules that define how they have to be acted upon, and then you have target groups or logically grouped application servers which are called as target groups, right? Which would basically be serving all those incoming traffic. Moving on, what do you mean by Envoy? Envoy is a CNCF graduated project. It evolved out of Lip, and primarily Envoy is written using C++. And Envoy is a reverse proxy that primarily operates in the layer 7. And it's pretty extensible in the sense that it has a filter based mechanism wherein you can chain multiple filters, more like middlewares in any API servers. Chaining them, you can customize Envoy to your own needs. And as you can see with the commits as well as stars, it's a pretty popular project. So what are some of the key features of Envoy? Service discovery, load balancing, and health checking, wherein you are able to take certain VMs out of rotation when they are unhealthy. Security, Envoy provides a lot of features around security. Observability, wherein you are able to track the different metrics around the number of requests served and other aspects around observability. rate limiting, where you are able to ensure that your backend servers are not overwhelmed by limiting the number of requests in a given threshold. And it's pretty extensible, as we spoke before. You can use multiple different filters to customize Envoy to it. So what are some of the key components of Envoy that we would be using in our custom load balancer? Well, these are some of the key components of Envoy: listener, filters, clusters, secrets, and upstream. Looking at this image here, you see port 443 and port 80. These are example for a listener, wherein our load balancer would listen on port 80 as well as port 443 for incoming requests, and there we could then move to set of chains, filter chains. These filter chains would include things like domain matching, custom components around. There could be Lua plugins that you can use to track incoming requests as well as maybe log them or act on the packet. Once these rules are applied on the incoming request, they are routed to the appropriate cluster. Right? A cluster is nothing but multiple upstreams, group of upstreams. An upstream is a single VM. As an example, it could be a particular single VM or virtual machine that serves your application. Right? A logical grouping of these upstreams would be a cluster for a given domain, for example, or a given path in a domain. And secrets would be used for managing or handling the certificates. This is a sample configuration for Envoy, a working example of it, wherein in this case we will be supporting traffic coming on port 80, and the domain that we are not restricting ourselves to any domain in this, which means that any traffic coming on port 80 would on the default route path would be routed to a cluster called some service, in this case cluster named some service. So, and the cluster some service in this case is pointing to particular IP address on port 80 with health check defined as seen here, right? with a timeout of 2 seconds and health check being performed at every interval of 5 seconds, and or failed health check would mean that it's taken out of rotation. So what are the requirements of our custom load balancer? Right? Some of the, that you could possibly add more features or more features that we could possibly support using our custom load balancer. But to begin with, we'll look at some basic features that we want to support. The primary one would be to distribute traffic amongst multiple different backend targets. Our custom load balancer should not be limited to any given domain. We should support supporting multiple domains. So we should have one load balancer that can route traffic to multiple different domains and paths among them. It should support health checking. That way we would be able to take out the application servers that are unhealthy or overwhelmed. We can take them out of rotation. It should be cloud agnostic in the sense that we should be able to run our custom load balancer or easily port it across multiple different cloud products. And we are looking at scalability customization. We'll see how we are going to do this. So this is the design of our custom load balancer. So we have some different components. As we can see here, we have a virtual machine which will be the custom load balancer that we have. So the idea is we would have a VM in which we will run our load balancer, and this VM will behave as the custom load balancer. And by making it cloud agnostic, you can easily run this VM anywhere. Right? You could run it on AWS, GCP, or even Azure. And as you can see here, we have our custom load balancer running within a VM, but it will be interacting with some other components which are outside the VM, like in this case an API server as well as a database. Right? So there will be a database which would basically store the configuration of our load balancer, like the domain, the incoming port, outgoing port, the IP addresses of the VMs, application VMs, as well as the even certificates, details related to certificates, etc. So we will have an API server that would fetch this data from the database and be interacting with our load balancer, which basically will be fetching this configuration and passing it and translating that into something that Envoy can understand. So as you see here, we would have a VM that would have two services that can be run as Linux systemctl services, for example. Like we would have Envoy running inside the VM, and we will have a control plane, custom control plane written using Go that would be communicating with Envoy in the form of gRPC communications. As we discussed before, Envoy supports service discovery, and we are going to do that using gRPC. We also have we'll also be using Cloud Init. We'll come to that. So I mean, this is how a sample Envoy service looks like. You would have the definition as in like aspect of this service configuration that we are interested in would be the configuration that we would be passing to Envoy when it boots up. As you can see here, we would be passing a particular startup config that Envoy would boot with. That way it knows how to interact with our. This is the configuration that we would want to bring up Envoy with. And these are some of the service discovery components of Envoy that we would want to. In this case, LDS config would be listener discovery service, and CDS would be cluster discovery service. So our Envoy would boot with these two discovery services enabled, and as you can see here, it would be using gRPC to communicate and discover these services. And in this case, we are going to tell our Envoy that okay, you should be communicating with XDS cluster, something that we call as XDS cluster here, which would, for fetching the configuration of Envoy, and be able to update dynamically without any downtime. What we mean to say is, if ever we were to add a new domain or remove a domain from our load balancing configuration, we would not want to restart Envoy or have any downtime to update the configuration. That would happen dynamically. And in this case, our XDS cluster or our control plane would be running on port 18,000 in the same VM, 127.0.1, as you can see here. And it can run on any port. As an example here, I have taken port 18,000. So our control plane can look something like this. It's pretty minimal in the sense that you have a go routine that would be running the Envoy server that would basically communicate with Envoy through gRPC and sharing the configuration that Envoy has to update itself with. And then we also have a sync server basically that would periodically talk to the API server and fetch the latest configuration. I mean, in this case, we would be polling our API server, but we can even use web sockets to improve the performance. And this is our this is the gRPC communication with Envoy, basically the gRPC control plane, right, wherein it would be updating the Envoy configuration. This is our sync server. That would mean it's a basic sync server wherein we have a for loop that's running on loop, and we have a select construct that basically uses a timer to periodically sync and get the configuration. And look, I'm talking about configuration. I mean, this is the basic entry in our database, right? Our DB could have a JSONV field, like if we were to use Postgres, wherein you would have some of these fields. As you can see here, you are saying okay, the domain that we want to support would be sandeepbhat.co.in, and these are the different VMs that are going to host this particular domain. And the incoming port and the outgoing port would be port 80. Right? The request would be coming on port 80, and the VMs would be supporting the same on the port 80 as well. And we have hijacks defined as you can see here. We basically can have multiple reports like this for different domains that would be passed by our load balancer to serve this traffic. So in terms of packaging, right, the Cloud Init is a key component wherein it's a initialization system or a package installation system. It supports writing custom scripts, and it's pretty cloud independent, as in you can have Cloud Init in AWS, GCP, and Azure as well. So particular Cloud Init script would be the same script would be supported across multiple different cloud products. So what this helps us do is, like, we are able to bring up our custom load balancer using Cloud Init. We would have a Cloud Init script which would run whenever the system boots up and be able to fetch Envoy and install Envoy as a service in the system, as well as bring up download our the binary of the control plane that we designed, and get them up and running as a Linux service. That way you are able to package them together. A sample Cloud Init script can look something like this, right, wherein the key thing to notice here would be the scripts user, right? What we mean to say is we would always want our Cloud Init script to run whenever the system, right? And with that, we can even support updating our system as and when we have a newer version of our control. The script would go towards the end of the script, end of the Cloud Init script. With this, we are able to now we have a custom load balancer that basically achieves all these aspects that we see here, right? We are able to distribute traffic among multiple different backend targets by orchestrating Envoy and dynamically without any downtime. And we support multiple different domains, health checking, and we are able to be cloud agnostic by using Cloud Init. And in terms of scalability customization, as we saw in our design, we can run our custom load balancer on any virtual machine, which means that if you are to run it on say AWS, right, we can run our load balancer on machine with a lower spec like say T2 dot small or T2 dot medium, or you could even run it on a bigger machine like say T2 dot x large or 4x large based on your needs or based on the traffic needs. Yeah. So I mean, I would also like to do a bit of cost comparison across AWS LB as well as our custom load balancer and as to why we would want to use our custom load balancer and how it's beneficial. AWS LB has hourly pricing, and it also has pricing or cost based on different aspects like number of connections, bytes processed, and even the active connections as well as the rules processed. And if you are to bring that up comparatively, I mean, it can look something like close to $16 per month. I mean, I'm not even taking into consideration the cost of traffic or data processed. I'm only looking at some of the basic cost components here. And if you have to look at a custom load balancer, it has hourly pricing per instance, right? The cost of running a VM, that we would have to only pay for that. And if you are to run a smaller VM, like say a VM with a smaller configuration, like say T2 medium or even T2 small, you would end up paying lower amount. And at the same time, you have the I mean, if you are to compare the cost of that, say running our load balancer on T2 micro, it would be close to around $8 per month. I mean, T2 micro we have seen to be pretty capable of handling traffic to a decently good enough scale. Now let's take a look at our demo. As you can see here, I have three separate terminals here. The one here is running Envoy. The one here is running the API server. I'm running my API server here, and this one out here is running the control plane, right? So ideally, in our load balancer, in any deployed in any VM virtual machine, would have these two components in it, the one in the top as well as the one in the bottom, and this one, the API server, would be running outside the system, and our control plane would be configured to talk to the API server. And I have also modified the etc host file of my system to the domain sandeepbhat.com to my own system, local host in this case, to aid with this step. So going back to the demo, you see here, right? I have two VMs that are running in AWS that are running nothing but basic Nginx server with a custom HTML file. It basically prints the IP address of the. And if you see here, currently both of the VMs are running, and I'm pointing to my domain Sandeep Bhat. So what would happen is when we hit sandeepbhat.com in Chrome, as per our etc host file, it's pointing to the same system as our system 127.0.0.1 in this case on port 80, which is how our load balancer is configured now, wherein we are saying, okay, as you can see in a previous slide here, our domain, the domain here is different, but we have configured it pretty similar to this one, wherein we are able to route any traffic coming on port 80 is routed to port 80 on the target view. So when we hit sandeepbhat.com here, it's routed to port 80 in the same system, wherein we have our system listening to it, and it routes the traffic to the target VMs, the demo VMs 1 and 2. And we'll see the IP address of the demo VMs being printed. So as you can see here, it's routing traffic evenly across both of them. Now, if you were to bring down one of the VMs, we should pretty soon see our load balancer routing all the traffic to the other VM. Right? The health check came into impact, and it's able to identify that the target VM is down, one of the VMs is down, and we keep seeing all the requests go to the same. Thus, I would like to conclude my demo. Hope you had as much fun as I had while doing this talk. Thanks for listening.